day, students. Today, let us work out a few problems in interference of light, division of amplitude, regarding experiments in Newton's rings and Michelson's interferometers. So the first question is, Newton's rings are observed in reflected light of wavelength lambda is equal to 5.9 into 10 raised to minus 7 meters. The diameter of the 10th dark ring is 0.5 centimeters. Find the radius of curvature of the lens and the thickness of air film. So first let us write down the given parameters. Wavelength lambda is given as 5.9 into 10 power minus 7 meters. The diameter of the 10th dark ring. So the number of the fringe n is 10 and the diameter of the 10th dark ring d10 is given as 0.5 centimeters. In meters, 10 raised to minus 2 meters. We have to find the radius of curvature of the lens and thickness of the air film. So refractive index here is 1. Here we have observed the dark ring. So let us use the condition for destructive interference or darkness. It is given as 2 mu t is equal to n lambda, right? And here the radius of the nth dark ring is given as Rn is equal to square root of n lambda r. We have this from the theory. Since the diameter is given here, let us write diameter of the nth ring as twice Rn, that is twice root of n lambda r. Okay. Now, in order to find r, we just need to isolate this equation in terms of r equal to. Hence, we write dn square is equal to 4 times n lambda r. Thus, r is equal to dn square divided by 4n lambda. Let us substitute the values here. We get 0.5 into 10 raised to minus 2 the whole square divided by 4 into 10 into 5.9 into 10 raised to minus 7. And this can be calculated. You can use your calculators to do the calculation. Kindly do it. You will get the radius of curvature of the lens as 1.059 meters. Now, to find the thickness of the air film, we use the condition for destructive interference. 2 mu t is equal to n lambda. Okay, so here the refractive index is mu is equal to 1. Hence, the equation becomes 2t is equal to n lambda, and the thickness of the air film t can be written as n lambda divided by 2. Substituting values, we have 10 into 5.9 into 10 raised to minus 7 divided by 2. And you will get the thickness to be 29.5 into 10 raised to minus 7 meters. Thus, the radius is calculated as 1.059 meters and thickness of the air film is calculated as 29.5 into 10 raised to minus 7 meters. Moving on to the next question. Newton's rings are formed with a monochromatic light between a flat glass plate and a convex lens when viewed normally. What will be the wavelength of light used if the diameter of the 20th bright ring is 0.56 centimeters? Here, the radius of the curvature of the lens is given, r is equal to 1.2 meters. So first of all, let us write down the given parameters. The Newton's rings is viewed normally, okay, and reflected light is viewed, okay. Now the wavelength has to be measured, and the diameter of the 20th bright ring is given, that is 0.56 centimeters, and n is of value 20. And here the condition for brightness is to be used. R is equal to 1.2 meters. Okay. So while doing the theory for bright fringes, we get the radius of the nth bright fringe as square root of 2n plus 1 lambda r by 2. Okay. Here the values of n will vary from 0, 1, 2, 3, etc. Okay. So the expression for diameter of the nth ring will be twice square root of 2n plus 1 lambda r by 2. Okay. Now we need to calculate the wavelength. So let us isolate this equation in terms of lambda. So for that we write dn square is equal to 4 times 2n plus 1 lambda r divided by 2. That is 2 times 2n plus 1 into lambda r. Therefore we get lambda is equal to dn square divided by 2 into 2n plus 1 into r. Okay, so substituting the values here, we can write 0.56 into 10 raised to minus 2 in meters, okay, square, divided by 2 into 2n is 2 times 20, that is 40 plus 1 into r, 1.2. You can use your calculators, pause the video and do the calculation. Thus, wavelength is obtained as 3.186 into 10 raised to minus 7 meters. Okay, so in the third question, we have a Newton's rings arrangement is used with a source emitting two wavelengths. Lambda 1 is equal to 6 into 10 raised to minus 7 meters and lambda 2 is equal to 4.5 into 10 raised to minus 7 meters. It is found that the nth dark ring due to lambda 1 coincides with the n plus 1th dark ring due to lambda 2. Find the diameter of the nth dark ring due to lambda 1. Given radius of curvature of the lens r is equal to 90 centimeters. So let us write down the given parameters. The source length has two wavelengths. Lambda 1 is equal to 6 into 10 raised to minus 7 meters and lambda 2 is equal to 4.5 into 10 raised to minus 7 meters. Okay. Now the nth dark ring due to lambda 1 coincides with the n plus 1th dark ring due to lambda 2. So let us write down, the rings are coinciding, right? Let us write down the expression for the diameters, and the diameters will be coinciding, okay? So the diameter of the nth dark ring is given as dn is equal to twice square root of n lambda r. Okay, fine. So here the nth ring, it is due to the lambda 1 wavelength. So dn is equal to twice root of n lambda 1 r. And the diameter of the n plus 1th ring is due to lambda 2. So we have twice root of n plus 1 into lambda 2 r. Okay. Here we see that dn is coinciding with dn plus 1. So this equation can be written as 2 square root of n lambda 1 r is equal to 2 square root of n plus 1 lambda 2 r. Taking square root on both sides and cancelling out 2, we get n lambda 1 r is equal to n plus 1 lambda 2 r. Let us substitute the values here and try to find out the expression for n. Okay, so here I have n into 6 into 10 raised to minus 7 into r, let it be as such, it cancels out on both sides, okay, and is equal to n plus 1 into 4.5 into 10 raised to minus 7 into r, right? R cancels out and we have 6n, 10 raised to minus 7 cancels out on both sides, is equal to 4.5 n plus 4.5. Okay, so here we get n into 6 minus 4.5 is equal to 4.5. That is, n is equal to 4.5 divided by 6 minus 4.5 gives 1.5, and hence this will be equal to 3. So we found the value of n. Now let us find out the diameter of the nth dark ring. So d3 is given as twice square root of 3 into 6 into 10 raised to minus 7 into 0.90 meters. Okay, so let us use the calculators. Doing the calculation, we get 2.545 into 10 raised to minus 3 meters. Okay, so the diameter of the third dark ring is 2.545 into 10 raised to minus 3 meters. It is the third dark ring due to lambda 1 that coincides with the fourth dark ring of lambda 2. The next question. In Newton's rings experiment, the radius of curvature of a lens is 5 meters and its diameter is 2 centimeters. Calculate the total number of fringes formed if the wavelength of incident monochromatic light is 5,500 angstrom. Also calculate the number of rings if the system is kept in water, that is refractive index 1.33. So in this experiment, we do it in air and water and we have to calculate the total number of fringes formed. Okay, so here what is given is we have this lens, okay, placed on a glass plate and the diameter of this lens is given. So we have to calculate the total number of fringes formed in this region. Okay, so the last fringe will be the nth fringe and its diameter will be equal to the diameter of the lens. Okay, so let's start from there. Now the given parameters are radius of curvature of the lens is 5 meters. The diameter of the lens is 2 centimeters. In effect, the diameter of the nth ring, last ring, is given as 2 centimeters. That is 2 into 10 raised to minus 2 meters. Okay, so here if it is in air, the refractive index of air is 1. So that is, doing calculations, we get the diameter of the nth ring as twice square root of n lambda r. Wavelength is also given. Wavelength lambda is equal to 5,500 into 10 raised to minus 10 meters angstrom. Okay, angstrom is 10 raised to minus 10 meters. So substituting the values here, or let us first isolate n is equal to, we get dn square divided by 4 lambda r. substituting values, we get 2 into 10 raised to minus 2 the whole square divided by 4 into 5500 into 10 raised to minus 10 into 5. So doing calculations, we get 36.36. Since n can have only integral values, we take n to be equal to 36. So 36 fringes, dark fringes, and 36 bright fringes are formed here in the setup when Newton's rings is placed in the air. You can try to attempt the next section of this experiment in water by yourselves. We shall do it later on in the class. Now in the fifth question, in a Michelson's interferometer arrangement, if one of the mirrors is moved by a distance of 0.08 millimeters, very small distance, 250 fringes cross the field of view. Calculate the wavelength of light used. So in the theory of Michelson's interferometer, Nmi, we have the expression to determine wavelength as lambda is equal to 2x divided by n, where x is the distance moved by one of the mirrors and n is the number of fringes crossing the field of view. So here the distance moved x is given as 0.08 into 10 raised to minus 3 meters. Okay, and the number of fringes is 250. So simple substitution gives wavelength lambda is equal to 2 into 0.08 into 10 raised to minus 3 divided by 250. This can be calculated as, you may pause the video to do the calculations, and it is obtained as 640 into 10 raised to minus 9 meters. That is, wavelength is equal to 640 nanometers. Now, in this next question, we have, when light is incident normally on a glass plate of thickness 0.5 into 10 raised to minus 6 meters and index of refraction 1.5, which wavelengths in the visible region of 400 nanometer to 700 nanometer are strongly reflected by the plate? So we are trying to see the reflected light from a thin glass plate. Okay, so for that we have to see the conditions. Check. So for that we have to take the conditions for constructive interference from a thin film, right? The glass plate is here acting as the thin film. So the conditions for constructive interference is obtained as 2 mu t cos r is equal to odd integral multiple of half wavelength, that is 2n plus 1 lambda by 2, where n can have values 0, 1, 2, etc. Okay, this is of importance. Okay, n is starting from 0, 1, 2, etc. Since light is falling normally, cos r will be equal to 1. Hence, the expression becomes 2 mu t is equal to 2n plus 1 into lambda by 2, where n has values 0, 1, 2, 3, etc. Now let us give the values of n for each case. So when n is equal to 0, we get the condition 2 mu t is equal to lambda by 2, right? So the condition of lambda when n is equal to 0, that is lambda naught, can be calculated as 4 times mu t. Doing calculations, you get this as 4 into 1.5 into the thickness is 0.5 into 10 raised to minus 6. This is calculated as 3000 nanometers. Okay. Now this doesn't fall in the region of visible regions. We need to find out the wavelengths in the visible region that is strongly reflected. Okay, this is reflected, but it is not in the visible region. Now, in the next case, for n is equal to 1, we get 2 mu t is equal to n is equal to 1. Hence, we have 3 times lambda by 2. So this implies lambda wavelength for n equal to 1 as lambda 1 is equal to 4 mu t divided by 3. Okay, so that is 3000 divided by 3 giving 1000 nanometers. Again, 1000 nanometers, it is getting reflected, but it does not fall in the region of visible light. Okay. Now let us take the next condition, n is equal to 2. Now this implies 2 mu t is equal to 5 lambda by 2, right? So we get the wavelength for n equal to 2, lambda 2 is equal to 4 mu t divided by 5. Okay, so that is 3000 divided by 5, we get 600 nanometers. Now this falls in the region of visible light. Okay, now let us give the value for n as 3. For n is equal to 3, we have 2 mu t is equal to 7 times lambda by 2, right? So the wavelength for n is equal to 3, lambda 3 is obtained as 4 times mu t divided by 7. That is 3000 divided by 7 gives, you can calculate it, it will be 428.5 nanometers. Okay, again this falls in the region of visible light. Okay, now when n is equal to 4, the condition will be 2 mu t is equal to 9 lambda by 2. So the wavelength when n is equal to 4, lambda 4 is given as 4 times mu t divided by 9. And this is calculated as, you can do the calculations, you will get 333.3 nanometers. Now this does not fall in the region of visible light. Okay, now if we continue for n equal to 5, 6, 7, again we will get wavelengths in the lower region. It will not fall in the visible light. So we stop here and we have identified the wavelengths from which are reflected from the glass plate. They are lambda 2 and lambda 3. That is, lambda 2 is equal to 600 nanometers and lambda 3 is equal to 428.5 nanometers is reflected from the glass plate. Now lambda 2 is around the red light and lambda 3 is around the blue-green light. Okay. Now with that, we have come to the end of today's discussion. Thank you.